Okay, dear participants, I welcome for this sixth day FDP program. And as knows, actually every day we are moving with two sessions, and today is the last day. So for the last day, we kept people actually from industry as well as academician, those who will actually share their thoughts. So first, and to introduce for this session number one, Mr. S. Senthil Kumar sir, who will talk about actually the advancement of advanced polymer composites for aerospace and mechanical applications. So Mr. S. Senthil Kumar sir actually is a co-founder and CEO of two companies. One is MS Wintech Polysol Private Limited is in Chennai, and MS Infineon Polysolutions India Private Limited. So he's the owner of these two polymer industries. And sir actually have a bachelor degree in mechanical engineering. Later on, he did his post-graduation in plastic engineering, and he has also his MBA, Master in Business Administration. His total years of experience is more than 25 years. And the last employment before his own industry, he was in DuPont India Limited in the senior leadership role. Senthil Kumar sir has held various leadership positions in the world's leading polymer companies, like already I told you, DuPont, then Royal DSM, Angel Machinery, with over more than 22 years of hardcore plastic machinery and polymers. In his previous employment at DuPont, he has led the business for their engineering polymer business unit for South Asia, encompassing the complete range of DuPont engineering polymers, covering several industrial segments. He was also part of the Asia Pacific senior leadership team at DuPont. Presently, Mr. Senthil Kumar sir is, as already mentioned, co-founder and CEO of Wintech Polysol Private Limited and Infineon Polysolution India Private Limited. He is also a senior technical and strategic consultant to many Indian and multinational polymer industries. He is a senior council member for a few global management and technical consulting groups, and also an eminent speaker in different plastic forums and associations. He is an active member of Indian Plastic Institute, IPI, in all India level as well as in the Chennai chapter. So, Wintech Polysol engaged with 4 different verticals. One is polymer distribution and custom compounds, stock shapes and machining, custom the parts. And MS Infineon Polysolution India Private Limited engaged with Greenfield is a consulting firm offering strategic consulting in the following areas: greenfield plant setup for plastic industries, machinery selection and assessment, particularly injection molding machine, extrusion and its accessories. Offers technical consultancy for product and application development, market assessment, volumes, projection mapping, strength, weakness assessment before setting the industries, customer preferences, compatibility assessment, etc. And prototyping, 3D printing, troubleshooting and process optimization. So with his vast knowledge on polymer and polymer industries, by working in different well-known polymer industries as well as with his own industry. So for this 1 hour, sir will give his own insight related to advancement in polymer composite, particularly in aerospace and mechanical applications. I welcome sir, welcome for this program, and now the stage for you to deliver.
Thank you, Behra sir. Of course, Crescent University is not new to me. I have, I think, come to one of your Plasterfest function maybe 5-7 years back. I inaugurated it, and this is the second opportunity where I am very happy to interact with Crescent University and its associates. So that's how it is. So first of all, thank you very much for the opportunity. So without much delay, let's go directly into deep dive into the subject topic, which is advanced polymer composites for aerospace and mechanical application. Today, if you see, whatever is applicable to aerospace is even applicable to automotive, because you need lightweighting for automotive as much as possible. You know, it is both for the IC engines, the internal combustion engines, as well as the electric vehicles, because electric vehicles, the battery packages are becoming bigger and bigger. So you need to make the other items lighter to accommodate the battery packs. So what is applicable for a rocket or a missile is today even applicable for automotive, and not only for automotive, for various other applications. Some of them I'll touch upon, and the segments which are very interesting, I'll touch upon and take you through in the next 45 minutes to 1 hour. So let's first go to the basics of polymer before we even start the presentation. So I think everybody is aware about the classic polymer pyramid, and this pyramid is centrally bifurcated. We have stretched a little bit, but centrally bifurcated into two major sects, which is amorphous and semi-crystalline. So right side you find the materials which are in the amorphous stage, and left side is where you have the right side is the semi-crystalline and the left side is the amorphous material. And typically the amorphous materials are materials which are more transparent. To easily identify the material, you will find the polycarbonates, the polysulfones, the polystyrenes, acrylic is all very transparent or translucent in behavior, by vision. So these all are part of amorphous. This is the easy way to classify. Semi-crystalline materials are normally translucent to opaque, and that's how it will be. From a performance standpoint, semi-crystalline materials are more engineered or used in engineering applications. Nevertheless, with a few exceptions, but semi-crystallines are widely used for very high chemical resistance, very high temperature resistance, very high in terms of overall mechanical performance, etc. The amorphous are more towards the commodity applications, the applications which have limited mechanical requirements, but there are some specific areas like translucency, the combination of transparency with certain few additional requirements where you don't need very specific chemical resistance or any other performance. This is how they are divided. But since I mentioned that we have stretched the pyramid a little bit, the center portion remains as the elastic member, which is conventionally rubber, but from a polymer standpoint, how do we bring that into our forum is that these are materials like TPU, TPE, TPV. TPV is thermoplastic vulcanicide, thermoplastic elastomers, thermoplastic ether ester copolymers, styrene, butadiene, styrene kind of monomers. So these are materials which are plastics but behave like rubber. So you have the best advantage of plastic. and yet it will also be very flexible and perform like rubber. So these are combination of materials available. So this is one. So before even we go to the material side, from a designer standpoint, what are the most critical areas where one has to look at? Because the topic of discussion itself is materials which are going into mechanical applications and aerospace and things like that. What are those critical aspects which we have to think before we even select that right material? So there are major aspects like material properties, the mold construction, the functional requirements, the economic factors, processing, aesthetics requirement, tolerance and all that. But fundamentally, there is something called product design. That is the most important aspect. So if you see the product design in combination with the functional requirement is what is most critical for performance application. Say for example, an automotive or an aerospace application, you don't require aesthetics, you don't require high gloss or anything like that, but it has to functionally meet the requirements like cryogenic requirement or super high temperature requirements. And all that in combination with a certain product design, because it has to be again molded and formed to a certain size. So product design in combination with the functional requirement is the most critical aspect when it comes to selecting a material for an application which requires high criticality. So we have listed down in this chart, I have listed down a few important applications which includes aerospace to automotive. So automotive is one thing which we see on a daily basis. So the criticality and the vulnerability of the industry also. The car has to become lighter and lighter to give more and more fuel efficiency. And it has to be lighter to accommodate the EV batteries as well in the coming years. So if you see, sometimes the criticality what is required for automotive may be even more stringent than aerospace in some cases. But what all is required for aerospace is required for automotive. So that is why I said we can't differentiate automotive to aerospace, except for a few exceptions where you have very high, super high temperature requirement like 400 degrees, 350 degrees, which are typically the case in terms of aerospace, but in automotive, not more than 250 degrees. And we are extensively participating in many of the automotive programs where the metal is getting replaced to polymer, and they can take temperatures as good as 220 to 250 degrees continuous use. So those are the areas many of our materials are being deployed, and we have given a very good value proposition in terms of saving cost on account of reducing the weight of the application. So some of the areas and its criticality. Some of the criticality is listed here. If you see on the left side is high rigidity, very high rigidity, very good toughness. Rigid and toughness are two kind of opposite parameters. One is being stiff, and one is stiff, but yet it will also be a little more flexible. So those two combinations are very clear when you test your material. When you test the tensile bars of material, you'll be able to clearly identify which is a stiff material and which is a tough material. Lightweighting is the key in almost all the segments listed above. We've said 5 different segments. And all the 5 segments have highest criticality and highest CTQ, critical quality requirement is lightweight. Chemical resistance, yes, in terms of automotive, not on all applications. The interior, when we say automotive, we are not talking about the seating systems or the interiors or the dashboard or the bumpers are all commodity applications in automotive. When we talk about automotive, when I mention automotive here, we are talking about something under the bonnet. Once you open the bonnet, there are at least 15 to 18 kgs of polymeric materials molded and kept as applications, and those are the applications which I am talking about. So a general term of automotive might be misleading, but I'm not mentioning about the dashboards, the the systems inside, the seating systems, the other consoles and things like that. They are extremely commodity, and even the commodity material can handle that as well. So this is all on the chemical resistance. If you see in automotive is high, in industrial applications, some of the industrial applications is high. Certain cases, hot water resistance, corrosion resistance is again one of the major area where somebody has to move from metal to plastic is to prevent from the part from getting corroded. So corrosion resistance comes by default. Opportunity to reduce cost versus traditional material. This is a very important statement, but it's covered in one small line. But then if you see, we have worked across hundreds of cases where plastic material, engineering polymer, which is costing anywhere between 300 to 2000 rupees, can replace a metal, either aluminum die cast or steel material, any of the metal, and still give a cost saving and overall a good value proposition. So if you want to know why, I can give you a case where if a gear in a transmission in an automotive, especially two-wheeler, has to be made, the gear has to be made in metal using 11 different processes. It starts with cutting of the metal, then it goes for shearing, shaving, hobbing, and further final finishes and all that. So from the time it goes as rolls stock to one place, it has to pass through 11 different operations or 11 different machines to come out as gear. So every single stage, it costs a lot of extra cost and money and time. So I can give you a case, but if you ask us, can we replace a transmission gear using plastic? My answer is no. We cannot change the transmission gear, which is conventionally in metal, and there is an amount of torque which is required. It cannot be made using plastic, but there are gears which are called idler gears in motorbikes. This is a real case study where idler gear of the motorbike, which is just moving between the forward and the rear, and just without much of torque, it is moving. It is just helping the motion alone with much lesser torque. Where we replaced a material which is costing about 2,500 rupees, a carbon fiber filled nylon, in lieu of 55-60 rupees a material which is typically a metal, mild steel, and still able to give a very good value proposition. And the customer, one of the Indian manufacturer, Indian motorbike manufacturer, is able to get about $1 per gear, and there are two gears in a bike. Of two idler gears in a bike, which is like 160, 170 rupees, they are able to save, and the production time is just 15 seconds, and just like that they can produce. And whereas the metal has to go through at least 18 to 19 days cycle to get finished from a bar stock to a final gear. So these are some of the areas where we have to take a holistic approach to get the part cost validated. The opportunity to produce innovative design, very unique designs can be made out of polymer as compared to any of the metal, because of this flexibility in terms of the design and the techniques in terms of processing. So some of the idea, just to give a rough idea, how much is the density of a highly structured polymer, in the sense if you want to have a 60% glass reinforced nylon, it cannot go beyond 1.75 to 1.8 grams per cc in terms of the density, whereas a copper's density will be somewhere close to 8.5. Steel, which is very commonly used, will be somewhere between 7.8 to 7, almost 8. For calculation purpose, we use as 8. So even aluminium, if you take, it is somewhere between 2.7 to 3.5. So this is, even at aluminium or magnesium, the structural polymers can give a very nice value proposition in terms of weight reduction. So it can still be 50% of the weight of an aluminum die cast a part. Of course, part has to be again fully evaluated, but whatever we see as an application, many of the cases that the wall thickness of aluminum given to the wall thickness of polymer later on taken and evaluated will be much lower. So with a 2.5 mm or 3 mm wall thickness, a polymer can fill very comfortably and still make the part very strong. So how do we make the part very strong? We are going to see that in the next couple of charts. I'll explain how it is made that way. So lightweight provides saving in many ways. It is the indirect savings are all like easier handling of parts, reduced shipment cost, and automotive fuel efficiency. So just to give a input that every 100 kgs saved in a car will give 1% saving in fuel efficiency. So just see the collective 1% may appear very small, for which you have to actually remove 100 kgs from the car. But 1% on a collective basis with millions of cars made, just imagine the kind of fuel saving it can have. So this is the target with which the industry is working on. And this is a kind of a benchmark which I'm giving you, that 100 kg saving in weight, a reduction in weight will give a 1% saving on the cost. So there are, what are the most important for applications? There are many important CTQs required, but there are some which are very critical from each material standpoint. Say for example, if you select an amorphous thermoplastic material, they soften over a wide range of temperature because they don't have a sharp melting point, unlike semi-crystalline materials or crystalline semi-crystalline material. So they have a range. So they softens and then goes on and on and on, and then it heals, and then it again melts. I can do the comparison straight away with the semi-crystalline material, where semi-crystalline material exhibits very sharp melting point, very good formability. Here in this case, a little poor formability, but then I'll explain you why it is that. And then good transparency, good opaque. Here in this case, it will be opaque mostly. As I mentioned, most of the transparent materials, you name it, and they are all amorphous polymer. Extremely poor chemical resistance, which I told you earlier. And here are cases where this is extremely chemical resistant. And depending on the polymer which we use, sometimes can be acid resistant, sometimes can be dipped in fuel, dipped in salt water, things like that. So there are combinations of different materials which are used for different applications. Depending on the application, we select that as well. Bond well with adhesives. Difficult to bond because they have very good chemical resistance, so it will also prohibit a little bit of bonding and adhesion. But there are today techniques available to bond, that is also possible today. Prone to stress cracking, they are extremely prone to stress cracking. So if you overpack polycarbonate, if you overpack ABS, they will tend to crack. If there are sharp corners, sharp notches, notch sensitivity is very high in terms of amorphous polymer. Little less in term compares, and resistant to stress cracking, so is extremely good in semi-crystalline. Poor fatigue resistance, this is very good fatigue resistance, and extremely good on wear and friction. From a wear and friction standpoint, semi-crystalline material are extremely good compared to the amorphous. So when there is an opportunity to select a right polymer, these are the things which have to come in mind. The other side, you find the imidized material, which are highly super specialty, ultra specialty polymers, which doesn't have a melting point. It can take 400 degrees, 350 to 400 degree C also temperature. Extremely high in terms of PV ratio, which is pressure velocity ratio. Very good chemical resistance. The pressure velocity ratio helps them in deployment in terms of bearing and wear and friction applications. So this is on the thing, and the potential material choices pertaining to each class of material, like the amorphous, semi-crystalline, and all that. In terms of amorphous thermoplastics, some of the materials mentioned here, As the performance goes up, especially the temperature, if you say in amorphous, you generally don't put amorphous material into a high temperature application, but there are cases where there are certain amorphous materials which can go into high temperature. So there the cost goes up. Similarly, if you take materials which are beyond nylon, say nylon, PVT, PET is one range. Beyond that, if you say PTFE, PVDF, PEEK, PPS, there are materials like LCP, liquid crystal polymer, polyether-imide, polyamide-imide. So all these materials are very high in terms of performance, very high in terms of temperature resistance. PPS can take temperatures as good as 200 and maybe around 230 degrees continuous use, maybe a little 10 degrees more in terms of LCP. And if you go beyond, you have PEEK, polyether ether ketone, which are extremely good in terms of temperature resistance and a continuous use temperature. Of course, imidized material I mentioned, they are super specialty, they are super expensive, and they are extremely, in terms of moldability, they are very, very special, and they are used only in typical aerospace defense applications. So these are these are some of the materials. So this is by temperature, use of temperature. What are the other areas? Some could be on the mechanical properties like the flexural modulus, the stiffness, and all that. So since we are talking about applications to be deployed in engineering, mechanical applications, and automotive and aerospace, these are some of the areas. So in the flexural modulus side, you have material in which is some polyether-imide, 30% glass fill, can exhibit something like 13 lakh in terms of PSI, in terms of flex modulus, and a PPS in the semi-crystalline material can exhibit somewhere between 600,000 level in terms of PSI of flex modulus. So when you flex modulus, when you put that and then start to give a load from the middle and the bending aspect, if you see, which is very, very critical from a mechanical part designing. So if you have to design a engine color cover, cylinder head cover, or anything like that, the flex modulus is very important. So that is why the reinforcements come in the picture. So when we talk about flex modulus, it is very imperative that unless and until the polymer is modified by some modifier, in the sense from filler to add reinforcement, the reinforcement is in the form of glass fiber or carbon fiber, or in terms of there are more innovative fiber technologies coming in picture. So predominantly it is glass fiber because it's the cheapest available, and there are now technologies which can cut the glass into higher level. So the short glass is one, the long glass fibers are available today, which will exhibit extremely good flex modulus. So the use of innovative reinforcement technology combined with high performance polymer platform, so we have to deploy a suitable material which can take these kind of high loads. So for example, we have material in polyphenylene sulfide, PPS material, with almost 70% filled, 68 to 70% filling, which is the filling is in a combination of glass fiber and mineral together, around 68 to 70%. And similarly in nylons, there are materials which are almost like 70% glass fiber reinforced polymer. In a lighter vein, we always say this is polymer reinforced glass, but then to this level of material is available, and yet it is made to use in normal molding technology, and it can be made into components as well. So this combination of innovative reinforcement technology in combination with high performance polymer platform leads to a significant improvement in structural property. So structural property in the mechanical aspect is the most critical aspect of any of the industrial application, automotive and aerospace. So for example, when an unreinforced polymer exhibits about 60 to 70 megapascal of tensile strength, a structural same with the unreinforced polymer, in terms of tensile modulus, the structural polymer will exhibit somewhere close to 370 when you fill it with reinforcement. It can go zoom past multiple times, and tensile modulus is almost like 590 when you do. So this is the most innovative way. We can't use polymer just as it is in many of the cases. And for any of these kind of applications which are very critically demanding, the reinforcements are must. And the reinforcements are chosen in a way appropriate which suits the polymer. At the same time, it also suits the application. There are areas where carbon fiber is used, where again lightweighting is required, and the cost can be taken by the customer or the application. General applications, glass fibers are the most common used ones. So in similar way, if you take the tensile strength to weight ratio, benefits through lightweight in terms of polymer, the mild steel will give 52, aluminum alloy 95, magnesium alloy 133. In terms of the ratio, the highest would be the engineering polymer. So up to if you see 163 times, this is the ratio of tensile strength to the weight ratio. So now you can understand why engineering polymers are more and more deployed in these kind of critical applications. So why I mean, in general, there is a very constant or probably a myth is that when we add solid weight, it gives strength, is the general notion, right? I mean, when we normally, work on metals, that is the case. Normally we add the wall thickness, we make the metal part more stronger, and the stronger word represents more thickness, more heavier and more solid, right? But in polymer, it is other way. Polymer normally, from a molding standpoint, there are very certain, there are very clear guidance and very clear methods which need to be followed, that we cannot add more and more weight to the polymer or weight of the polymer. Even if I like to sell more material, I cannot sell, I cannot add more material to the application. And the application has to be poured out in a nice manner that there is uniform wall thickness. At the same time, how the ribbing we give exhibits or probably magnifies the strength phenomenally. So if you see the first part on the left side, you have a part without ribbing, but you can consider these two edges as the rib. But at the same time, when you give a cross rib this side, the part performance goes by 1.5 times. But when you give a zigzag like a honeycomb, I mean, next one is honeycomb, but then if you kind of give a zigzag, it goes 13 times higher. And when you give the same one on the alternate side, it gives 27 times and 30 times. So the more the ribs, more it gives performance strength, and the torsional stiffness is going to add very, very high. So normally when as a designer, when designing a polymer, we don't add weight, we add more ribs, we give the structural members more importance than the polymer deployment, polymer usage itself. So even if there is less, if you see if you take the wall thickness of these parts, it will be not more than 2.2 to 2.5 mm, and still it will be extremely strong because of the ribbing given. So this is one of the key aspects which I wanted to emphasize. And time and cost saving through reduced number of processes. If you take a sheet metal process, from the time it is given as metal, it has to go to stamping, drilling, cutting, bending, assembly, painting, and then it is finished as part. Whereas the die casting, if you take the same thing, metal ingots to melt down, molding, finishing, painting, and comes back as finished part. There are many steps which we have not mentioned here, but the critical important steps are mentioned. But in case of polymer, it is only the three major steps, which is one is granules, which a molder will get it readily available, and it has to be injection molded, and it directly becomes a finished part. You don't have to paint the part because material doesn't need painting. And why painting was required there in the metal part is because of the rust, corrosion aspect, and that is not there. No further secondary operation in most cases is required. because you are drilling, cutting, drilling, the shaping of the part, all are done in the injection mold itself. And more the tooling technology is improving today to accommodate any fine level of design aspect, and that is covered in the mold itself. So the most times, 90% of the time, the part comes out as finished. So it has to be directly packed and sent to the customer. So this is another area where cost saving through much longer average tool life. So if you take an aluminum die cast tool that normally functions between 100,000 parts, which is 1 lakh to 1.5 lakh cycles, it can produce 1 to 1.5 for the tool or the mold life. In case of magnesium, it will be a little more double, which is 3 lakhs. Zinc, it is about 450. But the structural polymer can anywhere be between 10 lakh cycles. And there are cases which we have seen, unless there is major damage, the same mold is slightly repaired and then reused for even multiple million cycles, which we have seen. So if you take an application, say for example a two-wheeler launch, the most critical aspect for the manufacturer is that I have a two-wheeler booking of 100,000 two-wheelers of 1 lakh booking per month, and how will I make an aluminum die cast part which requires almost every month the tool has to be changed. So this is a critical area where if you take 10-15 years back, we went to many of the two-wheeler companies, they emphasized this particular change, and they started to show, because the last 15-20 years you can see the kind of two-wheeler growth. Today we are #1 in the world in terms of two-wheeler manufacturing, and that is because a lot of changes happened, and the manufacturing setup in an ecosystem like India is made in such a way that even they can ramp up in no time from production, from the launch to ramp up to 1 lakh or 1.5 lakh bikes per month without any concern. Is only because of deploying more and more polymer or plastics in automotive, and that has paved way for quicker launches and quicker deployment of quicker ramp up of the models. So this is a classical case. So imagine aluminum die cast part, the tool gets replaced every single month, whereas even not more than 2-3 years, they can run with the same tool. The other major advantages versus metal are design flexibility leads to better components which are more marketable. So because you have the full final finished part, longer part life due to better corrosion resistance, superior surface finish, integral colors. If you want to add colors to the part, you add a color master batch of the pigment that becomes integral color. There are areas where color coding is required other than the marketable items. Even in engineering applications, color codings are becoming more and more evident. So that is what it is. And the key requirements for your application becomes stiffness and strength, stiffness and impact strength, or is toughness a key factor? These are the questions to be asked before the design has to be started. How about stiffness to weight ratio? Do high temperature come in play? Are there any other property you need to consider? These are all aspects, but most important aspect, if you have to ask, is I can give you the best of the material in the world. Is the cost appropriate for you? That is the most important key aspect, because one of the finest material which we supply in bulk today is polyether ether ketone, and which is used in aerospace, defense applications, and also into electronic assembly lines like the cell phone manufacturing lines and all that. So there, the cost of raw material is anywhere between 10 to 12,000 rupees per kg. But then, will an automotive industry or will an industrial application accommodate that kind of a cost? Definitely no. I can give you the best stiffness in peak. I can give you the best impact in peak. I can give you the best toughness, all the super high temperature resistance. Very good. But Will the cost be accommodative? No. So in that case, cost is the value proposition is the key, and that is what is the key criteria for material selection. Despite all these aspects which are technically required, finally it boils down to at what cost I service the application and what cost I give the service the customer, and is that making any value proposition or making any commercial sense. So is the key. So apart from these 6 areas, you can take the cost as the most important area. So now we'll run through in the next 10 minutes, we'll run through different polymers and characteristics and what are the combinations available in characteristics. So we start with the engineering polymer, polyacetal. Polyacetal is about 65 to 70 years old material. Today, one of the best material in terms of the mechanical properties, a combination of stiffness, toughness. They are very widely used for areas which are extremely tough, very good chemical resistance, very good solvent resistance, very good fuel resistance, extremely low on moisture absorption. And if you take the material, polyacetal starts from probably 150 rupees. There are certain grades of polyacetal which are costlier, but then the commodity grades are all starting from the range of 160, 150, 160 rupees range. And in the right side, if you see, there are various types of options. We are also doing glass filling in terms of polyester. Polyester is extremely stiff, even in the unfilled range. And when you fill it with glass, it becomes super stiff and super tough. And all these combinations which are suiting the requirement of application, we can modify in the polyacetal resin. Some of the major suppliers are mentioned below. And polyamides, when you talk about polyamides, it's again nylon 6, nylon 66, nylon 12, nylon 46, so on and so forth, nylon 10, nylon 12, and so on and so forth. There are multiple applications in automotive, very critical applications in automotive. And they are very good in terms of electrical property, good heat resistance, good chemical resistance, extremely good, good dimensional stability, but with a caveat, with a disclaimer that the moisture absorption of any polyamide is high. So when the moisture absorption is high, you have to compensate for the dimensional stability, which has to be managed accordingly. If you say from unreinforced to glass reinforced up to 60%, there are carbon fiber filled materials, UV stabilized, hydrolytically stable material which can take the coolants, the engine coolants, etc. Of course, flame retardant grades. They are extremely good in wear and friction resistant requirements. They are also can be modified to make it conductive. So there are conductive additives available. Just to move out of the hard plastics, now these are the soft plastics which behave like rubber, but then they are plastics. So there are materials like if you take Shore 20, you have plastic material. It is very, very unconventional. Normally, if you see rubber is in this scale between Shore A is a rubber scale. Even up to Shore D 30, 40 will be always in the flexible scale. But up to from Shore A 20 onwards, the material are available. They can be injection molded, blow molded, extruded, and all that. What the type of material is like thermoplastic volcanosite, thermoplastic olefins, thermoplastic elastomers, which are based on styrene butadiene, styrene ethylene butadiene, thermoplastic ether ester copolymers. And in TPUs, which are thermoplastic urethanes, urethanes are in the two-component system as well, but also on the thermoplastic side. The thermoplastic urethanes are in multiple chemistries like ether chemistry, polyester chemistry, polyether chemistry, polycaprolactam chemistry, and so on. Melt processable rubber, there are interesting areas where you have nitrile with a PVC combination. It will give the best combination of a nitrile rubber. In terms of moldability, it will be behaving like a flexible PVC. And these are the thermoplastic elastomer. There are multiple families, various range of materials available. Polythalamide, again going back to the harder plastics, polythalamides are part of the polyamide group, which are called the semi-aromatic polyamides. They exhibit extremely low moisture absorption, a very contradicting to the typical nylons, which are moisture absorbing. The polythylamides absorb extremely low moisture, and because of that, the property drop post moisture absorption is extremely low. So, which is used for many critical high temperature applications. The material which will melt at 330 degrees. It can take continuous use temperature of anything more than 220, 230 degrees. And these are available with filling ranges between 25 to 50%, and they're extremely hydrolytic stable. So they can be deployed in areas where heavy chemical resistance is required. Moving to the performance polymers, unlike the nylons, moving to the next level where polyphenylene sulfide is the most important. We sell a lot of quantity of polyphenylene sulfide PPS material to the market. They are used. They are extremely chemical resistant. They are very high temperature resistant. 250 degrees continuous use temperature. Melting point at 305 to 310 degrees. They are used in super specialty applications. If you see the next chart, I can show this is a kind of a strip down of a car, and most of the critical applications are made out of PPS globally. And these PPS can take, as I mentioned, very high temperature, very high chemical resistance. It can be soaked in acid also. Nothing happens to the material. It is almost next to PTFE in terms of chemical resistance from a very deployable manufacturable material standpoint. PPS is one of the finest material available, and another best part is it sounds like metal. So when you drop a PPS part, if you get a metallic sound, it will almost be like metal. And metallic sound, it is none other than PPS material. And very critical applications. If you see these applications, they are not any and sundry. They are very critical applications in the automotive. So some of the parts which are in display, the EGR valves, wherever there are high temperatures involved, where are the high pressures involved, high chemical resistance required, all these are the materials used. So these are throttle bodies used out of which are originally in aluminum die cast. Now the entire part is replaced to plastic. Water pumps are now, the entire body is replaced with PPS. This is a starter terminal base. These are parts which we supply to the market, which are metal replacements. These are bushes on the left side, which you see, which are conventionally in bearing materials like copper, brass, bronze, gunmetal, LTB, phosphorbronze, or carbon, the raw carbon material, which are replaced with engineering polymers, different type of polymers, but this got a 3 different combination. The combination starts with selecting a polymer based on the boundary condition. There is an active lubricant, which is a permanent lubricant in the material, which is internally lubricating the component, and there is a filler which is giving the structural strength. The combination of 3 we play with the permutation combination of these 3 different aspects, but in each category you have multiple options. Say for example, in polymer you have about 40 different options. In fillers you have at least 7 to 8 different types of filler, and in active lubricant you have at least 8 to 10 different active lubricants which are deployable. So this is the combination by which we play around, make a compound, and with those compounds, depending on the boundary condition, we make these kind of bushes and bearings. So these are used in high-end applications. We also, as a company from Wintech Polysol, we do basic feasibility analysis, polymer identification mapping, product and tool design, prototype and 3D printing, process optimization, customer polymer solutions, localization of polymer compounds, and so on and so forth. We also are connected with, we are part of a lab which is available in Tirumudivakam. I strongly urge B.S.Abdur sir, you can bring your team. Anybody in this group can come and visit. This is one of the finest center where we have a complete re-engineering, reverse engineering facility. This is in Tirumudivakam. I am also founding director for that company. I have not mentioned that, but this is a setup where 100 crores fund has been given, and the first phase we have completed with 35 to 40 crores, which has got state-of-the-art 3D printers worth about 18 crores on SLS technology. And we also have the other technology 3D printers, which are miniatures, which are small machines for skill development, but then primarily industrial grade 3D printers, SLS from EOS. We have 2 machines, one for metal, one for plastics. We have a scanner, which is probably which is third in the country. There are 3 machines in the entire country. One of the scanners we have in our center in Tirumudivakam, and this is the center. This is where we can take the inputs directly for re-engineering or reverse engineering in case, and the inputs can be directly given, modified, and then given to 3D printing for printing to see the prototype parts. So that is also there. We also have a metrology lab kind of to measure the entire CMM. I mean, we have CMMs and other metrology lab. We are also giving skill training for college students and also people who wants a short-term training. We also do that. So this is a part. This is a this particular organization is called Precision Engineering and Technology Center, where Government of Tamil Nadu, Government of India have funded 70%, and 30% is by us, in the sense from the industry. And this center is now managed by 2 of us, founding directors, me and one more gentleman. And we strongly urge. We already have participation from academic, I would say, from the academic portion, like the Anna University, MIT, and Sairam Institute, and there are a few German companies who have participated. We also strongly urge you can sign an MOU and probably start, sending your students for visit as well as for the training program. So this is about us and a small portion of what we do and what segments we handle in terms of various segments is all mentioned here. And thank you very much for the opportunity.
Okay, thank you, sir. Thank you for your valuable insight for the audience.
Yes.
And I made a note of it, sir, because this Precision Engineering Center will be used for faculty as well as students.
Yeah.
So I made a note of it, and we'll move forward, sir. So now participants, if you have any queries, you can directly ask, sir. Participants. Any queries, Mr. Manish Kumar, Dr. Manish Kumar from or any other participants? Anyone? Friends, take advantage of the things, because the faculty, those who are from mechanical department or from aerospace, as sir initiated, know that means we are now going through actually to convert metals into polymer only, plus polymer composites. These are the things, these are the future of the things. That means in future you may not study much about, you are not going to use much about actually the metallic parts, or except actually because where actually high transmission power requirement is there, still actually development not happened for that type of polymer, as already sir told actually, because he gave the complete idea of actually which polymer, how much temperature. So, but maybe in future actually research will happen, and a day will come when actually our big gears also will be replaced by some of the composites. So please, you are free to ask at least some 2-3 questions you can take.
Good evening, sir.
Good evening, sir.
Sir, this is Manish Kumar I'm a faculty in HBTU Kanpur, sir.
Fantastic, sir.
Okay, so sir, your presentation was wonderful. I really enjoyed that one, and it is in very depth also. So, sir, I have one question. Do you provide some internship or the training something for the B.Tech students?
We do that in both. Of course, our company, we take children for internship, but at PETC, we are now trying to build a structured program for internship, which will be, clearly a 10 to 12 days program where they go through completely in terms of how the re-engineering happens, reverse engineering happens, concluding with the 3D printing. So we also have smaller, apart from the production machines, we also have smaller machines which are FDM, which are SLS, and also we have the other technologies available. So we will run through all the technologies, and we are trying to structure a program. And I think maybe it will be available in next 3 months' time. This the center which I mentioned is very newly formed. Last October, our Chief Minister, Tamil Nadu Chief Minister, came and inaugurated it. And since then, we started to work with the industry. This is primarily to help the industry to get to speed, because many of the countries see as a MSME, I cannot afford machines which are costing $1 million, which is 15 crore machine or 10 crore machine for experimentation. I cannot. But this center helps in terms of using this machine on a small rent, even for an hourly basis. So this is what we are trying to establish for the industry. But this, when we help the industry, unless and until we help the polymer students, who should be aware and take it to the next level, we will not help the industry. So we are trying to attach ourselves with the polymer companies or the polymer universities which are teaching chemical and polymer, and trying to associate with this center also. Of course, it need not be polymer. It can be any group like mechanical and any other groups which help in terms of the overall re-engineering and reverse engineering. So all these are available, sir.
Yeah. Sir, actually, our department is one of the oldest department in India. It was established in 1965.
Oh, fantastic.
And our institute, now it turns into university in 2016. Before that, it is 102 years old. It was established by one of the Britishers.
Okay.
His name was Harcourt Butler. So the thing is that this training part is for the third year students, because in our curriculum, we have 1.5 month training program. So we generally send students to some companies in North India.
Right.
So with the help of this conference, I come to means in contact again with the southern part of India. So that's why I'm exploring that part. So if it is possible for us, then we will talk later also in the upcoming months.
No problems. We'll do that.
Yeah, because this year the examination was over, so students almost they will return by 15th of July. So
Correct.
we can say the next year onwards we can think about that if it is possible.
Sure.
Thank you, sir. Thank you, Senthil, sir. Wonderful. Yeah.
Thank you, sir. Thank you.
Any other participants from our Chennai or nearby shoots, any queries? Because ours industry it is related with actually with the government of Tamil Nadu, as I told, no, that meant that particular facility inaugurated by Chief Minister of Tamil Nadu, as well as many things they are doing. Any other participants? Okay. If no other queries, I think we'll go for next. Thank you, Senthil Kumar.
Thank you very much, sir.
I'll be in contact, and I think I will come there for that. Our 4th July IPI program is also there, so I hope I'll meet you there personally also.
Sure. Sure,
Okay.
sure.
Okay. Thank you. Thank
Thank
you
you.
so much for your
Thank
time,
you.
sir. With
Thank
your
you.
busy schedule to take time and deliver lecture, I understood the things, but thank you. Thank you so much for
Thank you,
helping.
Nathan. Thank you. Thank you.
Okay, sir. Okay. Thank you.